Welcome to the Unit 12, Section 3 video on graphing and interpreting exponential functions.
Recall an exponential function can be described as ab to the x, but we're going to add a value to the end of this, which is your plus k. If you add a value or subtract a value on the end of the form ab to the x, then you are going to have an horizontal asymptote that is not 0. So if you don't have a plus k value on the end, your horizontal asymptote would be 0. But if you do have a value, that is the value of your horizontal asymptote. So graphing exponential functions, first you will want to draw a dashed line to represent the horizontal asymptote. You're going to need that line to guide what your graph is going to approach. Then make a table of values, and you want to use at least 4. Make sure you always include the y-intercept, or at least include it if possible. Be sure to choose negative and positive x values if possible as well. Plot these points and connect the points with a smooth curve that approaches the horizontal asymptote. So for example 1 here, we're going to graph the following exponential function, 3 to the x plus 1. So here's my table of values. You can plug in various values into this using a calculator to get your y value. You can also go to y equals on your TI-84, plug in 3 to the x plus 1 into your y1, and then pull up your table of values. And that's actually a better way to go, because it not only saves you a little bit of time in having to type in so many things, but it also allows you to look at all your y's and see which ones are going to fit your graph. And so I picked a few values that are going to fit my graph, and I have my horizontal asymptote of 1, and I'm approaching that value of 1 there on the graph. And as I plotted my points, I drew my smooth curve, and I approached 1 because we have a plus 1 on the end. That is my horizontal asymptote. So this graph does represent growth. Our horizontal asymptote is at y equals 1, and our y-intercept is at 0, 2. In this example, I pulled up my table of values. I found values that were appropriate to fit this graph. I plotted my points. You will want to plot your horizontal asymptote, which here would be at y equals 0, because there's no k value on the end. And you will want to connect with a smooth curve. So this graph represents to k, horizontal asymptote is at y equals 0, and our y-intercept is at 0, 4. In this example, we want to graph this exponential function. Just looking at the equation, the minus 2 on the end tells us our horizontal asymptote is at negative 2, so you'll graph that with your dashed line. You'll find a table of values that will fit the graph that you are given, and then you will plot those points and connect your points with a smooth curve approaching that horizontal asymptote of negative 2. Now, we have a growth function. Our horizontal asymptote is at y equals negative 2, and our y-intercept is at 0, negative 3.5.
Recall the starting value and a constant ratio were determined when identifying exponentials in the real world. A is your starting value, B is your constant ratio. When B is greater than 1, the function models growth. When B is between 0 and 1, the function models decay. So let's take a look at some examples where we delve a little bit deeper into the meaning of real-world functions. The function 2 times 3 to the x models an insect population after x days. What will the population be on the 5th day? So what you're going to do is fill in the blanks here to do a little bit of interpretation of this function. This function represents exponential growth because b is greater than 1. The starting population is 2, because that's our a value. The population is multiplied by 3, our b value, each day. The population will be what on the 5th day? So we're going to plug in 5 for our x, use your calculator, and get 486 would be our population on the 5th day. The population of Winnemucca, Nevada can be modeled by P equals 6191 times 1.04 to the t, where T is the number of years since 1990. So what is the population in 1990? Well, that is our starting value. That's the first year. That's our starting year. So we just look at our A value, which is 6191. By what percent did the population increase each year? Well, we'd like to take a look at our B value. And since we are doing growth, it is greater than 1. But the part of that growth or that B value that we are concerned with is after the 1. Okay, it's how much more above the 1 we are. So 0.04 is 4%. That's how much we increased each year. The population in 2005, you're going to plug in a value for T. Do not plug in 2005 though, because remember our starting year is 1990. So 1991 would be year 1, 1992 would be year 2. So 2005 would be year 15. You plug in 15, use your calculator, and you get approximately 11,150. Remember to round down because we cannot have a fraction of a person. The population of deer in Delaware County, Pennsylvania can be modeled by this exponential function, where T is the number of years since 2000. So what was the starting population of deer in 2000? Again, look at your A value for that, 2,345. By what percent did the population increase each year? Look at your B value. We are not concerned with the 100% part, so we don't care about the 1, but we do care about the 0.3. We're increasing by 30% each year. And the population of deer in 2019, since 2000 is year 0, 2019 is year 19, so we're going to plug in 19 for our T and get that the deer population will be approximately 342,820. Now that we've interpreted exponential equations, let's start creating them based on a situation. By identifying the starting value and the common ratio, a simple exponential equation can be formed. Once an equation is written, it can be used to model a real-world scenario. Remember, t is often used rather than x when the independent variable is time. So bacteria can multiply at an alarming rate. When each bacterium splits into 2 new cells, thus doubling, if we start with only one bacterium, which can double every hour, how many bacteria will we have by the end of the day? So let's let A be the starting number of bacterium, B be the multiplication factor for the bacteria, and T be the hours after the bacteria begins to split. So let's plug in A and B first so that we have a function that can be used for any time period. Okay, A is 1 because we start with one bacterium, B is 2 because it doubles every time period, and T is 24, which is our number of hours after the bacteria begins to split. Okay, so let's use our form, plug in A and B. A, of course, is 1, B is 2. So now we have 2 to the t, which can be used for any time frame. We're concerned with 24 hours, so we're going to put it to the 24th power, and that leaves us with 16,777,216. So that's how many we will have by the end of the day. Each year, the local country club sponsors a tennis tournament. Play starts with 128 participants. During each round, half of the players are eliminated. How many players remain after 5 rounds? Let's let A be the starting number of players, B be the multiplication factor for the players, and X be the rounds played. So A is 128, that's how many participants we start with, and each round we have the number of players, so our multiplication factor is 1/2. And we're going to play 5 rounds and see how many are left. So we take our form, plug in A and B to get our equation, and then we're going to plug in our X to find our value. So after 5 rounds, we will be left with 4 players. The first COVID numbers in South Carolina were given in March 2020, and 25 people in Horry County had tested positive. Every week, the number increased by 20%. How many people would have COVID after 30 weeks? So we're going to let A be the initial number of COVID cases, B be the multiplication factor of COVID cases, and T be the weeks after the initial COVID numbers. So A here is 25. That's how many had tested positive initially. Our multiplication factor is going to be 1.2 because we are growing here. So it should be a greater than 1. We've got to retain the number who have already tested positive and add 20% to it. So that's 1 plus 20%, so 1.2. And then we have T equals 30 because we want to see how many cases there will be after 30 weeks. So we're going to write our formula by plugging in A and B first. Then we'll plug in 30 to find out how many cases there will be, and it'll be approximately 5,934. So that is how many people would have COVID after 30 weeks, given that rate. When you put money into the bank, for example, a savings account, they pay you for the privilege of using your money to invest and to make more money. This is called interest. On the other hand, when a bank lends money, they charge you for the privilege of using their money that they could otherwise invest it. This is also called interest. When the bank lends money, there are 4 important numbers to be considered. How much money is being loaned? This is called the principal and denoted by a P. How long the money will be loaned out? This is time and is denoted with a T. What is the amount of interest being paid per unit of time? This is usually expressed as an annual percentage of the borrowed amount. This is called the interest rate and is denoted by an R. We're going to multiply all that information together to get the total interest paid over the life of the loan, denoted with an I. So I equals PRT, principal times the rate times the time. The principal and interest are added together to determine the total amount that will be paid at the end of the loan, denoted by an A. So if we do A equals P plus I, but we know that I is PRT, and we substitute PRT for I, and then factor out a P, we have P times the quantity 1 plus RT. And that is going to be our formula for simple interest, where A is the total amount, P is the principal, R is the interest rate as a decimal, and T is your time. And your time will be in years. So, the bank lends you $2,000 at a 6% interest rate for 1 year. What is the total amount paid on the loan? So we start with a principal of $2,000, and our rate is 6%, so that's 0.06. Our time is 1 year. So we're going to plug all 3 of those items in and find out that the total amount that you will pay on the loan is $2,120. So since you started with $2,000, you're going to end up paying $120 in interest. Suppose you borrow $2,000 from a friend for books, fees, and some supplies for the spring semester. The friend is quite generous and only charges 1% simple interest. You promise to pay them back after you have worked all summer, so the money will be borrowed for 8 months, January to August. How much will you owe them at the end of August? So our principal, we're borrowing $2,000 at a rate of 0.01, and for a time of 8 months. Remember, we have to express it as years. So 8 months out of 12 months in a year gives us a fraction of 2/3. So 2/3 of a year is the period of the loan. So we're going to plug all that information into our simple interest formula. And when we put this into our calculator, we end up getting approximately $2,013.33, of which $13.33 is the interest that you paid on that loan. Simple interest is most often used to compare different loan products and investment opportunities. But for many car loans, student loans, mortgages, investments, and credit cards, compound interest is used instead. Compound interest simply rolls the interest earned back into the account and recalculates the interest for the next period. So in other words, you're paying interest on the interest of your loan. Compound interest uses this formula to find out how much you will owe over some time period. So A is the total amount, P is the principal, R is your interest rate as a decimal, just like before, and T is your time in years. However, you now have an N, that is the number of times it is compounded in 1 year. So when interpreting compound interest problems, it is helpful to understand how to interpret how many times interest is compounded in a year. So if the wording says semi-annually, then your value for N is going to be 2 because it means it's compounded 2 times a year, or every 6 months. If it's quarterly, that's 4 times a year. Monthly would be 12 times a year, and daily would be 365 days a year. We're going to ignore leap year in this case. So suppose we invest $1,700 at 9% interest compounded daily for 5 years. What is the future value of the investment? Well, we start with a principal of $1,700. We have a rate of 9%, so that's 0.09. We're going to have the investment go for 5 years, so time is T, which is 5. And then compounded daily means 365 is N. So we're going to plug all of that into our compound interest formula, use our calculator to find that the future value of the investment after 5 years would be $2,665.98. You borrow $675 to pay for a tutor at 4.2% rate, compounded monthly, to be repaid in 2 years. How much will you owe? So our principal, what we borrow, is $675. Our rate is 4.2%, which is 0.042. Our time is T, which is 2. That is 2 years that we are going to repay the loan. And is compounded monthly, so N is 12. Plug that all into your compound interest formula, and you're going to find that you'll end up paying $734.04 back on the loan. Thanks for checking out my video in the Algebra 1 Honor Series. You can subscribe to my channel. I've got the next video queued up for you, and if you need to check out any of the videos in the course, I've got the course playlist for you here as well. Thanks for watching.